Good afternoon or good morning, everyone, depending on where you are connected from. So today, IFR is extremely happy to welcome Claudia Cenedese from Woodsole Oceanographic Institution, and she will talk about melting icebergs. And Claudia, the floor is yours.
Thank you. So first of all, thank you for inviting me to give this talk. And although I thought about coming in person, was a bit too much at this time of the year for me to leave Woodsole. So for those who doesn't know, Woodsole Oceanographic Institution is a nonprofit organization that is in Massachusetts on Cape Cod in the United States. And this work I'm going to present could not have been done by myself. Mainly was done by a lot of students, like that I list down here, and collaborators, especially Fiamma Straneo, that now she's here at University of at Harvard University, which she kind of entrained me into this project. And this picture on the background, we actually took it on a research cruise that we did together in 2018. And this beautiful iceberg that, to me, from the distance, we name it Cervino because it looked like that mountain. To me and Fiamma, that we're both Italian. So here we go. So one thing I want to tell to the students and whoever is listening, that if you have questions, please interrupt me and ask me a question. I always found myself that if I have a question in my mind during a talk, then I can't kind of follow anymore if there's a clarifying questions. So I'm happy to be interrupted. And also, I won't have time to go into details in a lot of things, but if you are curious about some aspect of this talk, you can always email me. Maybe, you'll find my email if you Google my name. Good. Okay, so why are we interested in glacier and icebergs? You probably know that both the Antarctic and the Arctic ice sheets are melting, and they're melting actually faster than in the previous years. And this is this plot. Can you see the little arrow moving on the screen? Yes, okay, good. So this is the mass loss of ice as a function of year. This is pretty old, but already there you could see that there was a dramatic increase of mass loss in the early 2000s. And one thing that people didn't appreciate, actually in Greenland, there was more mass loss than in Antarctica. And you can see this on the left page, which is a picture with color that indicates the speed of the ice sheet. So wherever you see blue or purple, even more, that means the ice sheet is flowing very faster than where it's, say, red. And as you can see, there are all these little purple dots near the coast, and those are glacier that ends, they're called marine terminating glaciers that ends in fjords, and that's what we're looking at, because once they terminate in fjords, they can calve and form icebergs. So that is kind of these left pictures in Greenland, where you form these kind of small icebergs, relatively small, because and they're called non-tabular icebergs, and they're formed by these ice streams that they're constrained. So there's a lot of stresses on the ice flow, and hence they can calve a lot, means they can be cut by the stress, and forms a lot of iceberg that are kind of relatively small in size. On the opposite, if you go to Antarctica, this is the right side of the picture, you have this ice shelf that have this long, we call it tongues, this long extension on the water. And in Greenland, they used to be like that, but these tongues broke a while ago, except for very few ice sheets in the north of Greenland. But most of the ice shelves are like that in Antarctica. And what happened is that because they're not constrained by topography, there's much less stress. And so they can protrude into the water at longer distance, and they break sometimes, but much less frequently. And that means the icebergs are much bigger. Like sometimes you see in the news that the big iceberg detached from Antarctica, and there are those large tabular icebergs that they can be as large as Manhattan, for example, some of them. So today I'll be focusing mainly on this non-tabular iceberg, just because Greenland is a bit easier to reach than Antarctica, and we've been focusing our work on those. But some of the principle can be applied to tabular iceberg, obviously. So the biggest difference when I say small and large, someone should ask me, compared to what? Well, one way to characterize this tabular versus non-tabular iceberg is the aspect ratio. And so if we call L, capital L, kind of characteristic size, horizontal size of the iceberg, and D, the draft, which is the part of the iceberg that is below the free surface, then we can define an aspect ratio, and that aspect ratio is very large for tabular iceberg, order of 1,000, because their length is much, much larger than their depth. And for Greenland iceberg, instead, this non-tabular iceberg, the aspect ratio is much smaller, between 0.5 and 50. And as you can see, they're more like they're smaller, but also like they're also is full of this what we call burgy bits, these little bits of ice that can be around bigger icebergs, both in Antarctica and in the Arctic. Okay, so now that we define these two classes, we'll focus on the non-tabular one. And before we go into melting, one thing we need to understand is how they move. So how they move is something that's pretty well known, and it's not kind of too hard because you can write what we call the momentum equation. So an equation, this top one, that regulates the motion, we call U, the velocity of the iceberg. So there are lots of terms, and I don't want to go into the details, but this is basically your MA. These are all forces on the right, and this is your acceleration. So what kind of forces is an iceberg subject to? So we have some things called the Coriolis force. That's due to the fact that Earth is rotating. We're going to ignore that because our fjord in Greenland are pretty small, and so the rotation of the Earth is a second order effect. Then we have some stresses, all this tau. So we're going to ignore the sea ice stresses just because the measurements we took were mainly in the summer, so there was not too much sea ice. And then the tau sub O and tau sub A are just the stress due to the air, if there is a relative motion of the air to the iceberg, and then the ocean stresses. And then these other forces can be due to waves or pressure gradients we're going to ignore. So to make it very simple, we're just going to look at these two stresses and see which one is more important to determine the acceleration of our iceberg. So we can do a simplified model, and what we found out, is that the main force, so we can say, okay, if you have an iceberg in steady state, so there's no acceleration, which one of these two forces is more prominent, or are they both important? So to do that, to understand which one in the real ocean was more important, Fiamma, Stranio, and others, before I went to Greenland, they went to this particular fjord, so which is in this orange box down here in Greenland. It's called Sermelik Fjord, and you have two pictures of it in the summer and in the winter. As you can see, in the winter is not possible to go there because there's too much ice. So usually Fiamma goes there every summer. Here there is a glacier on the left called Helm Glacier that ends here, and the calves. So up here is all ice melange, which are basically all iceberg but very close together because they're just been formed and they haven't started drifting yet. And then they came out of this part of the fjord, and then they flush out. This is the open ocean down here on the south, on the bottom part of this picture. And as you can see, in the summer, there's you can see a lot of large iceberg and some of the small. And so that's what we are going to look at. And in particular, to understand how they move, what Fiamma and colleagues did, they put something is called a pi sensor, this PIs, which is a pressure sensor equipped invert echo sounder. So there's a picture down here. That's what it does. So there is a little things that you put on the bottom, and then you have your iceberg moving on the top. And then it records, it emits bursts of pings every 10 minutes and records the first echo from a strong reflector, which would be, the strongest one will be if there is an object passing over the cone of influence of the pings, as depicted on the bottom. And you can see that by knowing where it pings, where the pings come, you can kind of determine like the draft of your iceberg. Not exactly, because obviously that would be the real draft if you went exactly in the middle. So it could skim on the side, but you can get kind of an order, better than an order of magnitude estimate of the draft. And then, as shown in these top pictures, what you can do, you can see having an iceberg that moves, that will be this gray square in this cone of influence of the pings. You can determine its velocity, because here is your iceberg, you get some data of the ping depth, and then basically by analyzing this data, you can get the velocity, because you know how long it took the iceberg to move along that path. And that's how we determine the velocity of 90 icebergs that pass in the summer over this instrument. And that was published in 2015. And you can see that we have the pings, and then at the same location, we had some measurements of the ambient velocity. So it's this color. So you can see here the velocity is negative on the top and a bit positive on the bottom. And then the top layer here, this red lines, is the wind speed. So if you put all these things together for 90 iceberg, then you get a picture like this. So this is representative 6 icebergs that are represented by this blue line. And the little dots at the bottom indicates the total draft. So this is the total draft of your iceberg. So some were very, 400 meters deep, and some were only like 100, as you can see. So there is a big variety of depth. But the important thing is that they all move in this ambient water. So, but what makes them move? So this red arrow, the continuous red line before, is the wind speed, scaled by a factor of 5. So you can see the direction. The location of this vertical blue line indicates the iceberg draft and velocity. So the location indicates the velocity. So for example, this iceberg here on the first panel on the top left has almost 0 velocity, while this iceberg here has a velocity of minus, say, 0.2 meters per second. So we know the velocity with the method I showed you before. And also this black line is your vertical velocity at that location that we observe with those ADCP, with another instrument put nearby. So we know what the ambient water, how the ambient water was moving. And this dashed red line indicates the approximate location of an isopictal, because in this particular fjord, although it's common in this fjord in the southeast of Greenland, there are mainly 2 water masses. The top water is fresh polar water, so it's fresh and cold in the top, say 200 meters or 180 meters. And the bottom instead is warm and salty Atlantic water. So that's the stratification, idealized stratification in our fjord. It's more complicated than that, obviously, especially in the summer, but say it's 2-layer. So what you can see is that the relative velocity of the iceberg, varies a lot in this location. And it's not necessarily even correlated, but we can say that it's not due to the wind speed, because you can see in this case, the wind was very large in these top 2 left panels. But the iceberg speed, for example, is very small, while saying it goes in the opposite direction, actually. Also down here in the bottom middle panel, the wind was in a positive direction and the iceberg moved in the negative direction. So what's going on? So think about this experiment. So you have a tank with an iceberg in the middle, right? And then you have the half of the height of the iceberg is subject to a velocity going from left to right, and the other half is subject to a velocity going right to left. So what do you think what is the iceberg going to do? Anybody wants to guess? One of the students, please. Okay, you're very shy. So the iceberg will not move, right? Because have someone pushing in one direction with one velocity, pushing with the same velocity in the opposite direction, the same amount of iceberg height, and so the iceberg is still. And this is very well shown in this experiment, in this data, where you can see that the velocity in this first panel on the left was mainly negative in the bottom part, mainly positive, roughly the same magnitude on the top part, and the iceberg basically wasn't moving. However, if the iceberg instead is all in the top layer, that in this case move, say in the bottom middle case, move on the left, then it moves with the water. So a very important thing that we not discovered, because this is pretty basic physics, but that was an oversight when we model iceberg, was that the velocity of the water on the surface is not necessarily telling us about the velocity of the iceberg. So what numerical model used to do before this study, and some of them still do, is to affect the iceberg. How they do it? They put the velocity, the winds is okay, but then they put the velocity of the water just on the first cell, on the top cell of the numerical model. So it's like putting this velocity up here or this velocity up here. And sometimes, like the middle bottom panel is okay, because the whole iceberg is embedded in that velocity. But if the iceberg is in a velocity shear means that there is a change in velocity over the draft of the iceberg, then one cannot just take into consideration the surface velocity, but has to take in consideration the integrated velocity over the draft. And that's very important, because again, your iceberg can go in the opposite direction if you don't take this into account. And so this is shown here mainly, that the velocity of your iceberg is better correlated with the ocean velocity integrated over the draft. So this is a depth integrated ocean velocity versus the wind speed. So at least in this fjord, for this data set of 90 icebergs, the iceberg moved with the integrated velocity of the ambient water. So we're moved by the ambient water, not by the wind, but not by just the surface water. So this is an important aspect that we try to stress to people that implement parameterization in climate model, for example, or general circulation ocean model to move icebergs. So again, important things, if there's shear flows, is to integrate it. Now, for the tabular icebergs that I showed you before, the one from Antarctica, because usually they're not moving in fjords, they're moving in the open ocean, or when the Greenland iceberg move in the open ocean, then it might be different, because that interface between two fluids might be deeper and they might not be subject to much of a shear flow, but one needs to check. So this is the first message of this talk. So if tonight someone asks you, what did that lady from Woodsall taught you today? So one thing is that iceberg move with the depth integrated velocity, and we need to consider that if you're trying to model this iceberg. Then, now that we know how they move, let's see how they melt. So this is a sketch of an iceberg that can melt in many different ways. So let's assume that there is, first of all, an iceberg relative velocity to the ambient fluid, right? So we saw that although there is an ocean current with velocity u0, the iceberg might have a relative velocity, means the velocity of the iceberg is different from the velocity of the ocean current, again, because the iceberg moves with the depth integrated velocity of the ocean current. And then it can melt by many, well, at least here, I described 4 physical mechanisms. So one is the surface melting. You know, the air is warm, it melts. That's like when you go skiing, if you do, or when you put an ice, drop some ice on the floor, then it eventually will melt just because the ambient temperature is warmer. But this is actually the least important mechanism. So this is where the melting is the least. Then there is some melting due to wave erosion. So if there are big waves, what happens is they'll be able to transport the warmth of the water at different height as they break onto the ice. And so there is this aspect too that we're going to neglect in this talk, because that's the most complicated one that hasn't been studied as well yet. And then we're going to focus on these 2 melting that they're called forced convection and vertical convection, buoyant convection, which though they're not very different. Basically, one is called basal melting and one is called side convection. But it's due to the fact that, again, the bottom or the side of the iceberg melt. And when they melt, what do? They form this what we call meltwater plumes, because the iceberg is formed mostly by fresh water, so it's zero salinity, and when it melts, it's at zero. Well, it's not quite 0 degrees because there is salt in the water. So salt water can freeze at lower temperature, but in this case, it's probably minus 1.8 C temperature. So that's the temperature of the water is cold, and so these plumes are actually buoyant. Means they have less. They're less dense than the ambient water, and so they move up. And basically, because in this part of the ocean, in a high latitude, what is important is the salinity, not the temperature. So although they're cold, they're so fresh that they kind of move up. And every time I talk about melt rate, just because I've been doing experiment, what I mean is by melt rate is the rate at which my ice-water interface, so say this wall, retreats in time. And so there will be a melt rate will be a velocity. So it's the velocity of your ice face as it moves, as it's moving inwards. If you want to know the total melt rate in terms of mass or volume, you need to multiply by the area and the density if you want the mass. So I don't want you to read this. I just want to say these are the parameterization. So how do we express mathematically these terms? And we put them in models, for example. And one thing I want to show you is that what we call the basal melt rate depends on velocity, on this relative velocity. So it's important to know how the iceberg moves relative to the open ocean, UO. While another one depends only on the temperature difference. So in this case, if you were to use this buoyant vertical convection for an iceberg that has a relative velocity, you would miss a lot of melting caused by this relative velocity. So it's kind of a mix of those two, but this aspect is much more important because you can think if an iceberg has a relative velocity, what happened is that these buoyant plumes can be, if the relative velocity is large enough, can be moved away from the iceberg face. And so you get straight contact of the iceberg with the ambient warm water. While if there is no motion, you have this plume that kind of insulate the iceberg from the warmer water outside. And so you have to rely on turbulence on this plume, like a chimney plume that entrain water to bring heat towards the ice to be melted. So it's very important, this relative velocity. This is another picture showing, possible melting at the bottom, all this solid color. And this wave erosion actually is interesting because you can basically, it's not a mechanical process. It's just a thermodynamic process because the ice melts because there is some heat. But because it's concentrated on the water line, what happens is that you can have this hanging cliff that every once in a while, as I schematically reproduce here, they can fall over. And I want to show you now, especially to keep you awake. This is of us, and we went to see that one of these hanging cliffs fell down. So you see, it's just down. And parents were just around there to take a measurement. So one has to be very careful for these hanging cliffs when you take measurements near icebergs. Okay, so this is a big overview, how the iceberg melt, how the iceberg move. So we saw this relative motion that was important because some parameterization, so some way to include this melting in models, already included that difference in velocity. But I want to understand better. So when I want to understand better a physical process, what I do, I mainly go to my fluid dynamics lab and I try to reproduce the process in a very idealized way. The ocean is very complex. So if I were to put something that represents a real iceberg with the real geometry, then there can be a lot of aspects that deceive you from understanding the basic physics. So I said, okay, the most simple iceberg is an ice, it's a square, or in this case, a parallelepiped that was 15 centimeters wide, 10 centimeters long, and 10 centimeters height. And what I did, instead of making the iceberg move, because again, if you do that, then it can, the flow is never perfect. So it can move around, it can hit the side. So I decided, okay, I'll keep my iceberg still and I make the water move around it. So it's a much more controlled experiment. And that is equivalent, I don't know if you have done Galilean transformation, to an iceberg moving into a water with a relative velocity. So here I have my source of water, my sink. So there is this velocity U, ambient velocity, that passes by my ice block. And so that U will be my relative velocity now, because the iceberg velocity is 0. So this is a picture of an iceberg from the side. So this is 10 centimeters the height. There is no relative flow. U is equal to 0. So what do we see here? So if you have very good eyes or a big screen, you can see this vertical meltwater plume going up and accumulating on the free surface. So it's a bit turbulent. So it's been diluted a bit going up. And then you see all these filaments of blue dye falling down. So the iceberg has been dyed with blue food dye. And what you see going down is because the ambient water, which is warm, is at 20 degrees, is getting cooled by the presence of the iceberg, because temperature diffuses much faster than salt. What you have is this water is getting colder. So it's cold and salt, so it goes down. But we're going to neglect that aspect, because in the real ocean, things are much more turbulent. So the main fluid will just go up. And now if I go a bit further, this experiment lasts a long time, you can see that, again, you got these big plumes going up, and most of the fresh water is on the surface. So I want you to remember that if there's no relative velocity, so if my iceberg was nice and still, most of the fresh water, meltwater, will be at the surface. And this is why people in the 70s thought that they could get, say, fresh water from icebergs. And they try to, and this idea is still going on now, that they can carry big tabular iceberg to Cape Town or Perth and kind of help the drought there. The problem in that idea is that these plumes going up are turbulent. They're turbulent in the lab, and they'll be even more turbulent in the real ocean. And what turbulence does, it mixes the water of the fresh water of the melt iceberg with the ambient salty water. So this water up here, if I were to measure their salinity, would not be 0. So that proposed mechanism to actually get drinkable water from iceberg is not feasible. So now they're thinking of changing the approach and maybe mining the ice, meaning having people going on top of them and just getting piece of ice and bringing it out. But that has all other problems, because these icebergs like to flip too. So anyway, let's think about melting. So here is melting, all the fresh water is on the top. Now let's see what happened when you put some velocity. So same experiment, but now the ambient velocity is moving at 3 centimeters a second from left to right. So you can see kind of the fluid going around the bottom, and you see a bit of a wake here. And the main differences. So first of all, I cannot see these meltwater plumes anymore. And the meltwater is not accumulating near the surface. So if we go a little bit further up, yeah, you see, there's no blue water on the surface. So what does that mean? Where is that blue water gone? Because the iceberg has been melting, you see, it's smaller. So when you have this relative flow, what can happen if this velocity U of the ambient fluid is larger than your plume velocity? It's like blowing a wind on your candle, right? If your candle, like flames velocity, is small compared to the wind, it will be basically you blow off your candle. And that's what is happening here. The ambient water is blowing off these plumes, and they're mixing it with the ambient water in the wake. And so all that fresh water now is not concentrated on the surface, but you can see slightly bluer over the draft of the iceberg. And this is fundamentally important. This is if someone asks you tonight what you learned from Claudia, this is the second thing. That when there is a relative velocity between the ambient fluid and the iceberg motion, and if this is very much larger than the plume velocity, this meltwater plume, what happened is that this fresh water is distributed over the entire draft. So if you model these iceberg, usually, you can model even a real iceberg, in a climate model, because they're too small compared to your grid cell. So you parameterize everything. So you tell them what to do, how they melt, etc. And then once they melt, you have to decide where to put that fresh water. Right? And people have been doing these experiments, numerical simulation actually, where all the fresh water, say from the ice sheets, is just put on the free surface, right? So they put they said, okay, the Greenland ice sheet is melting or is losing so much mass per year. Let's put all that converting to fresh water around the ice Greenland on the top cell of your model. And that would be a very big mistake, because first of all, if you put so much fresh water on the top, if it's not real, what we'll do will prevent exchange in the vertical water column, or what we call convection. So we'll change dramatically how things move vertically. And this experiment is showing you that that might not be the case. It might not be in the first cell at all. So you really have to be careful when you parameterize the melting to put the fresh water due to the melting at the right level. Because in this case, you'll have a fresher kind of water column, not just a fresh surface, which can change the dynamics of the ocean dramatically, because it can, in one case, prevent deep convection, in the other, not. Okay, so now if we put this in numbers, so we measure, this is called subglacial melt rate of your iceberg. So each cross is an experiment, and tell me how many centimeters per minute is melting. So this is our melt rate. And this is our relative velocity. So what you can see is that when the velocity is small, again, this relative velocity is small, the melting is fairly constant. And that is because these turbulent plume are doing the job. So they're entraining ambient water, but it's a not very effective way to bring heat towards the ice. But when the velocity is larger than your plumes, then there's another regime which is much more effective at bringing heat, because then depends basically directly on the velocity of the ambient fluid, on the relative velocity, that is affecting heat towards the ice and bringing all that heat. So then it's directly proportional to your relative velocity. And you have some sketches down here that I showed you before, when in this case A, the plumes are both attached and they accumulate this fresh water, although we understand it's not quite fresh on the surface. And in this case, C, instead, they drag it and mix it with ambient water all over the draft. So this is we propose a change in parameterization, because the previous parameterization was this straight line and then dashed going all the way to 0. Because you remember that parameterization where I showed you before here, depending on the relative velocity and the relative temperature and the length of your iceberg. But this relative velocity basically is saying that when the velocity is going to 0. But that's not quite true, because there's still a temperature factor. So this is kind of a bit of a mix of both. And also, there is the plumes velocity that here is important, because that determines how much entrainment there is. And so we proposed this with Anna Fitzmaurice, which was a student with Fiamma and I. We proposed this modified parameterization, where the velocity is the relative velocity of the iceberg when that velocity is larger than W, which is the vertical velocity of the plume. But when that relative velocity is less, so your velocity, your candle can stay up, then the important velocity is the velocity of the plume and the temperature of the plume. So I don't have time again to go into the detail, but this is important, because you don't want to have a parameterization, the bottom one, which is the previous one, that tells you that there is no melting if there is no velocity, because that is incorrect, because there's still this plume that can bring heat towards the ice and melt it. Not as effectively, but they're still there. So this is this improved parameterization that we proposed. And this is a picture some of the picture from before, showing you in red when this relative velocity is really important. Because again, in this case, where in all these red patches, there is a velocity difference between the ambient and the iceberg, and so things will change. Fresh water will not accumulate on the top and will be distributed all the way over the draft to the iceberg, and melting will be much faster. That melt rate will be faster. So including this parameterization, we get to numbers that are closer to what was observed in the ocean. Okay, so now I want to show you how do we take these measurements. So this is just to show you this cruise that we did in August 2018, where I was there. And to survey iceberg, it's not simple, right? Because you can't go close by. I can't, a human cannot go close by because it's too dangerous to go close to iceberg or even more dangerous glacier faces. So we use remote vehicle. So one we call it ice yak, is this kayak that is remotely operated. So we send this one. We had a little robot, again, with a wire. So it was, again, remotely operated, or some drones. So this is the picture of our cruise, where this is the jet yak. You see down here on the bottom right, you'll see coming our ship. So from the ship, we took measurements like velocity with an ADCP, so this acoustic profiler. Then we put the jet yak between the ship and the iceberg, roughly 100 meters from it. Or maybe, no, sorry, 100 meters was the ship and 50 meters was the jet yak. And again, this is because they wouldn't let us go any closer than 100 meters to the iceberg, because you saw the picture before, the movie before, there were these hanging cliffs everywhere, there's these undertows from an iceberg, so it's very dangerous. So this jet yak took measurements of velocity, temperature, and salinity within 50 meters. And then if we want to go very close to the ice, we had this other little robot. Here I'm going to show you before the measurement taken from the ship. These are multi-beam measurements. So you send a ping from the ship to the ice and record how long it takes back, and so you can know the distance, and then you reconstruct it. And these are the raw images of one of the Cervino, that iceberg. Actually, I show you the first slides, so you can see how an iceberg looks on the side. The hard things about this instrument is that if there is a convex cave inside the iceberg, you won't be able to see it because you only measure the first return. And this is a picture instead taken with a little remote system, ROV, this little robot that went very close to the ice. So we could, again, with a joystick, it's like playing video games, really. We could make it, he has a little camera, so you know where you were, you go underwater, and then you go very close to the ice. So sometimes we put something like this. This was a CDD, so measuring depth, pressure, conductivity, and temperature. And sometimes, just because I'm an experimentalist, I want to put some dye and see what happens, to see these meltwater plumes. So that's what this video shows. So this is a syringe. So we kind of push against the ice, so the syringe releases the dye, and you can see this dye gets diluted. So again, the plume is turbulent, so it's not laminar, so that means it entrains some salt water, that's why we cannot drink it, and it slowly come up. And just a little back of the envelope calculation showed us that that was kind of the correct velocity that we expected. Okay, so now we talk about icebergs that were what we call pure, clean, beautiful. Let me see what time it is. But I want just to tell you that things are a bit different when there is some sand in it. So iceberg, sometimes they're dirty, although dirty seems a bad connotation because they're beautiful when they're dirty, but they can have these stripes of sand in it. And you can see this is a person on a little kayak or little powerboat. It's 2 meters. So these stripes, they're roughly 1 meter to 2 meters thick. And how do they form? Well, they can form because ice, a glacier ice, the bottom part is in contact with the earth, so it can entrain some sand and rocks from that. It can happen in these Greenland fjords because from the side, there can be erosion, they can drop on that, It can happen, for example, when there's a volcanic eruption, all the ashes fall. So there are different methods. And then the way that you see them in the ocean, though, doesn't have to necessarily correspond to the orientation of formation, because again, the small icebergs are not stable and turn around. So again, I want to understand how this happened and what's the influence of sediment on the iceberg melting. And so we conduct an experiment in the lab. This is our GFD lab. This is an 8-meter flume. And what we did here, instead, we moved the iceberg just because we had land in the water. And then we construct iceberg like this, where we put some ice on the bottom, a sediment layer, which has glass beads and water inside. And they are randomly packed, so roughly 60% concentration, and then ice on the top. Now, if you put this in the laboratory and make it move, that's what you have. This is a little movie of it. So when the sand is very fine, you create this downwards now, because sand is much, is 2.5 times heavier than water. So it forms these sand plumes that are heavier in this case. So you have the melt plume going up, the sand plume going down, and this part where the sediments are melts much faster, and sometimes it can break up. So that's a mechanism by which an iceberg could break into 2 pieces, as you can see in this movie. We did experiment varying a bunch of parameters, and the important things I want to focus is that the melt rate, which, sorry, here I call V and here I call U, but this velocity is not really dependent on the width, so how much sediment I put within the 1 to 3 centimeters that I test in the lab, but it's very much dependent on the radius of the sediment. And why is that? So let's think. So I have this iceberg with this layer of sediment. So first of all, if it was just a layer working with a relative velocity, I would expect that layer to melt faster, if nothing else, because there is less ice in that layer, because 60% of that volume is constituted by glass. And so the ice should melt faster. But if that was the case, since the packing fraction of spheres, or pretty much any material, unless you get to some specific shapes, is independent on the size of the grain. So the packing fraction is 60%, no matter if my little sand is, 100 microns or a centimeter. And so should not depend on the radius. But what depends on the radius? Well, this is a picture with the iceberg that we took out to show the particles that were larger. This is one of the largest particles that we use. And what happened is that the melting depends on the size, because it generates this dense plume of particles. So there is a number, we call it non-dimensional, because we try always to look for dynamics that to understand which one is stronger, so we can then bring these results in the real ocean. So this non-dimensional number here is, which I call P, is the ratio between the settling velocity of my particles and the velocity of this dense plume formed by it. So you can think, if the dense particles velocity is much faster than my plume velocity, what would happen? The dense particle will just come out of the plume, and so will not generate much buoyancy, negative buoyancy, and turbulence. If my particles are very small, instead, their falling velocity, this V sub s, is going to be smaller than my plume velocity, and so they're going to be in the plume for a longer time and contribute to this negative buoyancy and generates a more turbulent plume. In simpler word, if I have very large diameter down here on the right, my little balls, what they will do, and what they did, they just fall one at a time, top, 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 and they didn't generate basically this dense water plume. While if they're smaller, as I showed you in this picture, they generate this negatively buoyant plume that again is more turbulent, brings more heat towards the ice, and melts it faster. And so that's why we have this increase in melting due to the turbulent dense plume formed by the particles. So here on the y-axis, we have the melt water, the melt rate non-dimensionalized by this U0, which is the melt rate that you would have if there wasn't the plume. So the melt rate calculated just by, say, how much will it take to melt, 40% of ice in a 60% matrix of glass sphere. So that's the number one. So you can see that if you put fine sand or something that has a very small settling velocity compared to the plume velocity, you can melt up to 3 times faster than if there wasn't this dense water plume. So again, the sediment enhances melting by a factor of 3 by generating this dense water plume when their settling velocity is small compared to the velocity of the plume. So I don't want, I think we're a bit over time, but and this is a summary of the biggest, all the findings that we had. But basically, 3 things again. If you want to know the velocity, how an iceberg moves, integrate the velocity of the ambient fluid over the draft. That's the important things. If you want to know where it melts and where the fresh water goes, look at the relative velocity again, because if there is 0 relative velocity, all the seemingly fresh water goes on the surface. Otherwise, it goes all the way over the draft of the iceberg. And third things, if there are sediments, they might enhance melting. First of all, because there is less ice to melt. Second, because there is this dense water plume, and if the particles are small, it might enhance the melting by a factor of 3. And the third mechanism is because if it breaks into 2, as I show you in the movie, then there's more surface area. It might melt faster just because of that. So thank you very much. And the little picture for iceberg moving in green. So you see the iceberg are now still. They keep moving around and rotating. So, okay, thank you.
Thank you very much, Claudia. Thank you very much. So the floor is now open for questions. So you can unmute yourself and ask a question or put something in the chat, which I will read with my French accent. Alik?
Well, thank you very much for insightful talk. It's quite, yeah, because I am not expert in glaciology, and that's exciting to know. I have a few questions, but I think you mentioned about the tides, and I really would like to understand which type of tides. Is it just the water tides, or it's a general this Earth's tidal oscillation, which we experience every day, something like a 30 centimeter, and how such kind of vertical movements will really generate or influence the flow. But another question is also related. You showed in experiments that you use some underwater icebergs. But if it is there is some air part of the iceberg, how is this air part influence because of the let's say now it is a 3-phase, yeah, not only water and ice, but also water, air, and ice. How it could influence? Maybe it's a very small influence to these things. Another thing, when you are doing a parameterization and so on, what about the boundary conditions there, like a Stefan, conditions and so on, to see, or latent heat when release, how much is the latent heat is high to affect on melting of ice. And finally, maybe it's something related about the time scales. You show us there's a melting process, but it's what is the time scale actually? How long? Because you thought it was a long experiment, and if you are now converting these all parameters to the real world, and is how long will be the process of, let's say, reducing of the roots of the ice, let's say by 50%. How long it will take? I mean, it's how fast is melting in general, if salinity, I mean, it's appropriate for the ocean, let's say. I mean, it's like that.
Okay, I'll try to
Maybe
respond.
many questions, but
Yes,
still,
I'll try to respond.
grab those for which you immediately can answer. And that's
So
it.
for the tides, actually, I didn't consider tides, but if the tidal motion of the ambient water generates a relative velocity, then your U0 will be your tides. So whatever generates relative velocity really doesn't matter what generates it. So if there are kind of a barotropic tides, if there's something that makes the iceberg go up and down for whatever reason, maybe because it just turn around and it's bubbling or bubbling, other reason, that would again, we should think about, will that motion destroy the plume or not? So again, if the vertical motion is much stronger than your vertical velocity, it would destroy the plumes and then bring more heat towards the ice. So I think no matter what the relative flow is generated to, one always has to think about, is this relative flow, either horizontal or vertical, going to be destroying those kind of insulating plumes? If they do, then there is direct advection of water towards the ice, and then you should use that parameterization that I suggest. That was a Wicks and Campbell. And so I'm going to back to that parameterization. So here, this parameterization here, that was proposed by Wicks and Campbell a long time ago. And what I changed was just define the relative velocity. So when the plumes are winning, that relative velocity is the plume velocity. Now, you asked me
about the latent heat and so on, how much it influences on melt.
So this parameterization here, I don't have time to go through it. I didn't have time to go through it, but this was derived by Wicks and Campbell by looking at the heat exchange of a flat plate in a uniform flow. So that was the boundary layer, generated by the heated plate. So it was the heat exchange by the heated plate in a uniform flow. So in the derivation of this simple parameterization, there is all the latent heat and thermodynamics that you were expecting. So it's all hidden in this one. And in particular, this value of kappa is different in the ocean in the lab because we have different Prandtl number and Reynolds number, which for the students are different value of the advection versus viscosity, the Reynolds number, and the Prandtl number is different values of transfer coefficient, like a turbulent viscosity or, what brings momentum and scalars around. So everything is hidden here. And this parameterization is being used for the ocean with this value, because if you put all these numbers that, inside there is a Reynolds number, a Prandtl's number, a Nusselt number, that's what it all derives. And in the ocean, in the laboratory, instead, we put this value, and this very good fit with the laboratory experiments, just by changing that kappa. There is no other fitting factors in our model. Okay, so that's the tides, that's the heat flux. Remind me.
Time scale, maybe it's about the time scale of melting.
Okay, so the experiment here was in the in a laboratory at 20 degrees. The reason is because I've done experiments in a cold room, at 3 degrees, like temperature of the water that you will find these fjords, but it's much more complex doing everything in a cold room. Electronics don't work as well and everything. And since the temperature dependence of melting, because it's again, thermodynamics is well known, I decided, okay, forget the cold room, let's do it, because I'm looking at the advection effects on the ice melting, not the temperature, because the temperature I think are much well known. And so this experiment were run for like 15 minutes, because after 15 minutes, I don't even know if this is, 14:30. Yeah, this is the end of it. So in 15 minutes, in a 20 degrees tank with that velocity, you melt the iceberg. And so all the experiments were done at 15 minutes, even if it didn't melt, because we want to compare apple with apple, the melt rate in 15 minutes. Mm-hmm. In the real ocean, it obviously is different because it will take much longer to melt. And what I can tell you, I can't tell you how long will it take for an iceberg to melt by 50%. But in our cruises, when we went to measure this melting by looking at the side, at the top, at the whole volume, we were there for 3 weeks and we took measurements a week apart, and we could determine a melt rate that was outside some noise level. So that meaning that in a week time, there is enough melt rate that you can measure it. So, you know, I don't remember, depends on the icebergs, where their position, how big they are, you know, like the relative motion, etc. But it's appreciable. In a week time, you can measure it. So that's the things I can tell you. And then there was a fourth question. I forgot.
Probably that was all. Yeah,
Okay,
because some
good.
other people also would like to
Okay,
know.
yes,
Thank
great.
you. Thank you.
Yeah.
Great. Yes, Claudia, thank you.
Okay, so we have a question in the chat from Sylvain, one of our PhD students. So thank you for the nice presentation. Q1, could you elaborate on how the Coriolis effect affects the movement and melting of iceberg in polar region?
Yeah, actually, I think if I go back. So this is something that we did with a student a while ago. Let me take the pictures of it. Okay. So I think it's this, yeah. Okay, so to study that, what we did, we put an iceberg, now it's a round piece of ice, on a rotating tank. So that's what we do in the lab. We see the effect of rotation on advection, in this case, melting, thermodynamics of objects, by putting in a rotating tank and rotating it faster than actually the Earth rotates, because we want this force to be comparable to other forces. So we did that. And so for the motion, Coriolis influence anything, even us, if we were big enough or fast enough or slow enough, actually, in our motion, is by moving things to the right in the northern hemisphere and moving things to the left in the southern hemisphere. So again, the ice will feel the effect, but because the water feels it too, again, it's all about its relative velocity. So if you have an iceberg that is going from Antarctica north, even if there weren't any currents, it will slightly turn left. The problem is, like, that is ideal, because then there are the currents that are generated and that they move, say, around Antarctica, because there is this Coriolis force on the water masses. But it's more interesting looking at the melting, because what happened when you have Earth rotation playing a role, and so in this case, let's think of these tabular icebergs that are big enough to feel Earth rotation. When they melt in an ambient fluid, a relative fluid, like we did this in the tank, by just spinning up or spinning down the tank, you can create a relative motion between the ice block and the ambient water. You can create a flow around an obstacle. And I don't know if you guys studied in fluid mechanics, there is this beautiful theorem called the Taylor-Proudhon theorem that tells you that if you have a uniform flow, not uniform, but if you have a flow around an obstacle, you create this column where there is no motion. So basically, there cannot be any vertical velocity. You can prove that mathematically. And so you get these columns. So although, like the classic experiment, if you put a puck, a hockey puck, or a little obstacle on the bottom of the tank, you glue it there, and then you spin it, you'll see the water going around it, not just where the obstacle is, but all the way up to the free surface. You generate this beautiful column when rotation is important. And so we want to see the effect of these columns on the melting. And indeed, when we put this ice block, you could see that, so this is the left is the theory part. But if you see the picture on the bottom, you can see that there were some part where there was a lot of melting, you see here, and all these lines where there was a lot of velocity. So again, advection, the plume detached, a lot of advection of heat, melting. But there was a part of it that didn't melt very much. And this corresponds to the location of the Taylor column, where there was not any relative motion then. And so there was not much melting. So that's what can cause. Then you might think, oh, is this going to happen in the ocean though, right? And Anna Fitzmaurice, for her PhD thesis, her last chapter was actually running numerical models of tabular iceberg. And she observed, even in her numerical models at geophysical scales, that this can happen. to some extent. Again, it might not occupy the whole size of the iceberg, because that depends on this Rossby number that tells you, this Rossby here tells me the velocity of the fluid, so how important is advection versus rotation. Obviously there are the currents and things, but she observed a hint of this process happening also at the numerical simulation that had the real scales. So those are the two main things. One is that your iceberg will be deflected to the right in the north hemisphere or left, but the water will too, so it's not that you're going to see a relative motion. And second is that Taylor column might prevent melting in some part of the bottom of the iceberg.
Thank you. So there was a question Q2. The size of iceberg, 10 centimeters by 10 centimeters you use in the lab is too small comparing to the real world situation. How do you deal with temperature gradient for this case?
Okay. I think this might be two questions. One for one for the scale. Again, what I tried to mention before, you look at this non-dimensional number. So for example, this Rossby number, which is U over FL. So again, is U over L is the time scale of your main flow, and 1 over F is the time scale of rotation of the planet. So there is a length scale here that tells you how, my length scale in the lab are smaller, but this is how I bring them back to the real ocean, by having this non-dimensional number. So that's how we do it. Again, my iceberg is small, but the melt rate should not depend on the size. It's just advection of heat. If is how much latent heat you can bring to the ice to melt it. Temperature gradients, we assume that in the ice, they're not temperature gradients, so that the ice is all at one temperature. In the real ocean, there might be some temperature gradients, but they're not very close to the interface, or the temperature gradient are very small, the gradient, right? So the center of your iceberg might be a -15, but this edge is at 0. So there is a temperature gradient in the ice, which one should take into account. But because I'm looking what happened in the interface, this gradient is very small compared to other effects like the latent heat. So we neglect that. Although in the real ocean, there is a small effect on that. And in terms of what I was thinking, yeah. And in the ocean part, the temperature gradient depends on your plume turbulence. And again, that's the Reynolds number. That's the non-dimensional number. Now in the laboratory, they do say, well, they did prove that if you get to a Reynolds number of 10,000, then the turbulence is well developed, and there shouldn't be any big difference even with the real ocean or atmosphere, which you have numbers of more of 10 to the 9 or 10 to the 8. However, in the lab, this experiment, we don't get to Reynolds to the 10 to the 9. So the ambient stratification, horizontal, temperature gradients might be slightly different. But again, we're thinking more in terms of heat fluxes. So not necessarily, the heat flux is due to a temperature gradient. So, but again, if you know that your temperature gradient in the ocean, then you can obtain a heat flux, and then from that, calculate how much melting you have. So I think that's the way we deal with the difference that you can have between the lab and the ocean.
Thank you, Claudia. So there is a question by Ibrahim Barry. Is there any concrete indication on as to how salinity of surface deep waters affect the rate at which the iceberg melts? If yes, don't you think it will be worth it to constrain the salinity of the waters using, for example, microthermometry?
Okay. So if I understand the question, the salinity of the water is important only because it determines the heat flux, right? So because it determines that temperature difference, and hence the heat flux that you can provide to your ice. If you have ice in fresh water, just because the fresh water, if you freeze it below zero, if you bring it below zero, then it's ice. You can only take heat up to a delta T of your temperature of the water minus zero. If you have salt, and depends on the salt concentration, you can bring that number zero below zero, right? So salt water usually at this latitude freezes at minus 1.8, and that's why you put salt on the roads and when it's cold to lower the temperature, freezing temperature. So salt is important for that principle. We assume that in the ice there is no salt, so it's not salt gradient, so there is no salt flux. But the salt does determine the heat transported to the iceberg. I'm less clear about why would the deep water matter. So did I now understood the question? Because if the deep water has some characteristic, but it's not in contact with the iceberg, then it wouldn't affect it. But maybe I misunderstood the question.
Maybe, Brian, you can clarify. No.
Yeah, can I say something?
Yes, sure.
Yeah. Well, normally when you have salinity, you have, it depends on the concentration, you have gradients from the surface water to the deep waters.
Yeah.
And it's supposed to affect melting because of the chloride content or the fluorine content, there's fluorine in the water. So I was asking myself, if you say you have a very thick ice that has a very, like you said, that has a very big depth, if you could get a chunk of that, then study the fluid in the ice, maybe you'll be able to understand how much is the salinity in the deep waters and salinity in the surface waters. And then you can model that and try to understand how that affects the melting of the ice.
Yeah. So we know how it affects the melting of the ice because of what I said before. But I think what you're saying is like, can you, by looking at the vertical melting of an ice, you determine the salinity, your profile? Yeah. So in theory, yes, I think that's a very good point, that if your salinity changes because of that T0, basically in that parameterization, in this parameterization here, actually the T of the ocean is, would change because this is the freezing temperature of water. This is a function of salinity. So obviously your melt rate will depend. I tell you the truth, I never thought about how much would it, what difference in velocity, but it's just a question of making a quick calculation would affect. The problem is that it's much simpler to measure salinity than measure vertical melt rates, in the real ocean. So I think if you want to know what the salinity of the ocean is, it's much easier to just put a probe that look at this. But it would have an effect for sure on the melting. Again, I don't know on top of my head how much.
Okay, it's beautiful. Thank you.
Yeah. And I think okay. Is there any other question?
Yeah, maybe. Is there any other question? Our students, Filippo, yeah?
Okay, hello. I'm not a student, so I don't know if I'm allowed to.
Yes, you are, Filippo. Everyone can ask a question.
Okay, so thank you. It was really interesting. And I have some curiosities since I'm not an expert in this, but we are working, just to quickly introduce, I'm working in a group, we are dealing with tsunamis. So, and also tsunamis generated by calving events. So we are studying this, we have some instrumentations, we are trying to understand, to measure them. So a curiosity is on the question you did at the beginning, if you have the wind and you have the velocity, and you were asking what happens, and you said that the iceberg stands still, But I was thinking more on a flip, because you have a momentum in this. Is it common or not? Probably not, because maybe the emerged part is smaller than the submerged one. So how frequent is the flip of the iceberg also in your experiment in the in your laboratory, in the laboratory?
Okay, so in my laboratory, my iceberg cannot flip. I prevent them flipping.
Yeah, I see the first one, it was fixed. No?
Yeah,
it was
but even the one that I move is still on a bar, and I move it with the bar. So, and I did that on purpose because that complicates things, obviously.
Yeah, I imagine that you have a parameterization, that if you have a flip, everything changes.
Yeah.
No?
However, we did do some experiments that they've been analyzed. That was last summer with a summer student fellow, like an undergrad student that she came, and we did some experiments to understand how frequent this flipping occurs, as you said. Now, the flipping, what we know now is depends on the aspect ratio, right? So if you have a very big, large L compared to H, it's not going to flip. Your tabular iceberg don't flip. If it's very small, a skinny rod up there, it will flip and will never stay stable. But you can, based on the geometry, calculate the stability of the iceberg. And what we did, actually, we did these experiments that we didn't use ice, again, to simplify. We used a plastic that has the same density as ice, though, 0.91 gram per centimeter cube. And we made a cylinder. So we only had two modes. A bobbing, it could go all up and down, or it could flip. And what we did, we kind of give him a little bit of an impulse, horizontal. So if you want to think about that, I don't know if the wind actually can flip them, tell you the truth, because 90% of the iceberg is below. But you can think it could be a tsunami. We're thinking about wave in general, not right? To flip it. So how much force do you need to put, right? Because if you put little force, if it's marginally stable, it will come back to its original position. But if you push it enough, it might flip. So we quantify that. And the idea is, which maybe we should talk after or late, another day, is if I force, so you can determine the mode of oscillation of the iceberg. So you can see which frequency does it oscillate. And we want to put a resonance. So if we shoot a wave to the iceberg with the same frequency as is resonant, is natural oscillation, will we be able to flip it? Even with not huge waves.
Because there is a sort of resonance, so an amplification of the oscillation. Yes. Really interesting.
That's what we're studying, one. And second thing is could we determine the melting? Because obviously we have different cylinder, different height, different aspect ratio. But if you know what is above, right? So that's the idea. And then we put some instrument on top to measure this oscillation. Can we determine in time how much is melting? Because if the shape changes, right? If it gets, you think an iceberg, and then it gets slowly, like my experiment, more vertical than horizontal, eventually this oscillation will change this frequency. And so to determine the melting just by looking at the oscillation of the iceberg. So we are kind of going in that direction, as you said, but it would be interesting to know if you have measurements of wave and iceberg flipping, because we're trying to reproduce that in the lab with this analysis.
Because because there are what we have seen that there are, for example, very different mechanisms also of calving, and each mechanism has its particular peculiar waves generated. So each mechanism of calving, you have the fall, the buoyancy, uplift, you have the turning. So every mechanism generates different waves. So it's very interesting.
And that's why, when I went to Greenland, two things I was surprised being a theoretical person or labs person is one, how many, I thought I could see, say, my background flow, right? So how hard is to see where the surface water goes, right? There are always this little piece of ice. I'll look at them, I'll determine that. No way. I could see, a meter from the ship was going not a meter, say 10 meters from the ship was going one direction and 20 meters the opposite with apparently no difference. It's like, what? So the ocean is complicated. And second is that these icebergs are never still. Every once in a while you look around and one flips, the smaller ones, the big ones. And you think, what induces them to flip, right? But again, it could be that there are even small waves that, they're not necessarily detectable if you measure, but they're not like tsunami kind of waves, could maybe trigger some resonance and then make it go. As you said, right, there are a lot of different kind of waves in a fjord generated by a lot of different processes. So I think that's a very interesting.
Yeah, indeed. And just another very quick, I don't want to take all the time. Is there, because you showed us some techniques to monitor the motion of these icebergs, you tracking them. Are there other techniques, for example, from remote sensing and so on, so you can also measure how this iceberg moves? Not with direct measuring, but I don't know, with satellite or some similar techniques that you can.
So there is this paper here. Sorry, I'm going back and forward. This paper here, Edelin and Hamilton, 2014. So Edelin, Hamilton unfortunately died in Antarctica a few years ago, but Edelin, she used photograph of the fjord, and then did something like we do in the lab, PIV, see how much it moves, and determines both the movement, and because this satellite's image could give him the height of the water, the height of the iceberg above water. There were special images, I forgot what they were called. She could calculate how much they were melting, right? So the DMSAT, I forgot, but I think on that paper, you can see how she did it. The problem that these images are very expensive because they have to have plane flight and take these measurements. But basically there were images that could tell her where the iceberg was and how tall above the water was. And by seeing how that changes in time, she could measure both the motion and the melting. She had to make some assumption, for example, what's the shape, right? Because that determines how much water, how much ice there is on the surface. It's a cylinder, it's a conical, and she did estimates for kind of.
Yes, I was asking this because we have the possibility to measure the sea level oscillation. We have a tide gauge. We have some seismic. You have a seismic network in this fjord, but what we miss is the validation. No, we don't know how. We know that there was something. We can measure the oscillation of. So a tsunami was provoked by the ice, not the touching, but we have not the direct measure or yes. So if you want to build some parametric correlation among between the water, let's say, or between the seismic signals and the origin, the source of this perturbation, we just need to quantify how big is the iceberg, the quantity of the ice that we touched. And it is not easy to find. Also, the one you were showing at the beginning, the pies, I think something like that. I don't know if that one was used to track the iceberg, if I understand.
No. It was fixed. So
fixed.
It was
Okay.
Yeah, it's fixed in a location, so it was only tracking the iceberg as they
passing
were
over
their but it was in a fixed location. So
yeah. But I think if you can put this close to the the glacier, and then you see how much ice is passing over this.
Okay. That could be. Yeah, the problem is like if the iceberg is too deep or is scarce, then your instrument is gone. So it is a balance between where you want to put them and going too close to the iceberg, to the glacier, that's the problem. That it's harder to actually deploy because you need to have an iceberg that goes through the melange. And also if there is iceberg that are still very deep.
Very interesting. I will stop the question because I will I will contact you.
yeah, because I want to know where you're working and
it was very interesting. Thank you.
Send me an email. That's great.
Okay.
Thank you, Filippo. So I just wanted to ask a very quick question, which actually it was related to this aspect ratio. I was just curious to know if, I know you said at the beginning we're going to look at tabular iceberg, but I was curious to know if you tried this experiment with different aspect ratio of the iceberg. Because I wanted to put this aspect ratio somehow in the parameterization.
Yeah. Okay. So I have a paper with another GFD fellows that we study. This one. Okay. Does aspect ratio matters? So here. So does it matter? Yes. It does matter, especially if you want to have a global melting. number. So if it say, oh, this iceberg is in this background flow, how much melts? Then the aspect ratio is important. So Esther, he has a paper in Physical Review Fluids. And all this work that I'm saying, if you guys are interested, I've wrote an annual review, annual review of fluid mechanics, where you can find all these references. If you look at me and Fiamma Stranio, we have this annual review of fluid mechanics and iceberg melting, and all these references are there. But what Eric discovered is that, sorry, so these are different velocity and different aspect ratio by making it different length. So we had 5 different aspect ratio. And he found that, he found that basically the most melting happened at the front, which is not surprising. So the first phase that encounters your iceberg. So the front has the most melting. The bottom melting was not uniform because at least in the lab, we have this detachment and formation of eddies, which again are another mechanism by providing heat. So this red line is the melt rate in a numerical simulation. So you could see more melt rate where this eddy formed. It did some of that numerically. And also the things that melt so the front melt the fastest, then there was the bottom, and then the size in the back. So but all different sizes had a different kind of melt rate. In fact, the bottom was almost half of the front one. Or we kind of did it, the front and the back put together, they were twice as much as the bottom. So if you look at Eric, it does, I don't have the slides now, but he did measure melting in all different phases and the bottom and quantify. So it's definitely different. So if you want to have iceberg of different aspect ratio and you want just to have a bulk melting, you need to take into account the aspect ratio because as you can expect, if you have a tabular iceberg, most of the melting will happen on the bottom, right? Because that's the biggest surface, but that is a full melting compared to the sides.
Yeah, so, and you will have just a little plume, like
exactly.
They will not be super efficient.
Yeah, exactly. While when you have this Greenland iceberg that have much more height than width, there's much more melting on the side, and so per unit volume or per unit area, they melt more. The Greenland, the one that they have. And
also I mean, if it's tabular, you're also in this surface layer, which is already a boundary layer, and
well, it depends on how deep is the tabular iceberg, but yes, there's not much to evolve. But then you can create these currents underneath, these rowdy currents that can have turbulence anyway. So, so definitely there is a whole, these studies are people one.
Okay, thank you very much, Claudia.
I want to answer the last question that now I remember. The first person asked me a question was about air in the iceberg, because that's a question that actually a lot of people ask me. What's the influence of air bubbles in the ice? So if you know the fraction of air, again, the fraction of ice is 1 minus how much air there is and how much sediment there is. So you can calculate the melt rate, how much ice there is if you know how much air there is. And so your melt rate, again, will be your latent heat, your heat flux divided by the density of the ice, the latent heat flux of the ice, and the volume fraction of the ice in terms of melting. Now, though, if you have bubble, they might create plumes too, like ice sediments. So there is a study done by Rebecca Jackson on the effect of bubbles. I don't know the top of the head where it is, but some people have studied the effect of bubbles on iceberg melting beside their fraction, occupying that fraction of ice. So, okay, all done.
Okay. Well, thanks again very much. So some people are saying very interesting in the chat. But yes, Claudia, thank you very much. It was a brilliant talk and lots of questions.
And please email me if you want to hear more or without a question. I remember for the students, there's not such a thing as a stupid question. If you have some question, just email me and we can either Zoom or I'll send you, if it's an easy reply, we can, just do it by email. So it was really a pleasure to give this talk, and thank you for inviting me again.
Thank you. Thank you very much.
Bye. Have a great day.
Yeah.
Thank you very much. Bye-bye.
Bye-bye.